Yep.
Okay. All right, so I'm going to be talking about Hasktorch, so a Haskell library for machine learning with type functional programming, and in particular, machine learning with neural networks. So even those of you who may not be in the machine learning field may have seen demos like this. There's a lot of new capabilities that are coming up in computer vision, in natural language processing, in other areas that really are only possible to do with neural networks as of now. So it's worth thinking about, how do we implement these sorts of computations, and are there ways in which we can express these sort of machine learning models better? So how do we implement these sort of models today? So most of this work is done in Python in the machine learning field. So using imperative programming, using object-oriented programming. And one of the most popular and powerful libraries to do that is called PyTorch. You can think of PyTorch as having sort of two main capabilities that are intertwined. So in one sense, it's a numerical computing, scientific computing library with a lot of mathematical operations that operate on ND arrays. In machine learning, they're sometimes referred to as tensors, even though mathematically they're not quite tensors. So that's kind of one piece of it. So doing kind of a numerical computing library. And then the second aspect is that is this ability to do automatic differentiation for all those mathematical operations. And that's what makes it also a neural network library, because automatic differentiation is the basis for computing gradients to do optimization and learning in neural networks. So fortunately for us, PyTorch is built on top of a powerful C++ backend library, also called libtorch, that implements all of these mathematical operations, implements automatic differentiation, and a lot of other functionality, serialization of models, and really can be used as a standalone C++ neural network library on its own. And that's kind of the starting point for Hasktorch, which is we start with code-generated Haskell that creates the C++ bindings. And Junji, one of our collaborators from Japan, gave a great talk about this at ICFP last year on all the details about kind of the kind of internals of the library, C++ interface, and so on. You can check it out on YouTube here. But just the raw C++ bindings, it's not a very kind of Haskell-oriented experience. So on top of that, we build higher level API interfaces. And we kind of have two tracks there. One is with untyped tensors, so a little bit more like Python, where you just have kind of a tensor type. And then another alternate path where we type the tensor dimensions. I'll say a little bit more about that later. And on top of this kind of higher level API, then we implement machine learning models on that. So before I could go further into the use of Hasktorch itself, let me just pause for a second and think about, like, why isn't this happening already? Why don't we already use functional programming for machine learning? And I'll say a little bit about this differentiable programming term in just a bit. But so why don't we use functional programming for neural networks? And so, one thing. So these are kind of points of conventional wisdom about why sort of imperative programming, object-oriented programming is kind of a more natural representation. So one thing is that models, maybe they lend themselves more to object-oriented programming. They have parameters that you have to fit, and they have computations that are dependent on that parameter. So maybe that kind of fits into, you have member variables as your parameters, and then you have kind of methods as your computation. Second, these mathematical operations are all kind of ND array input, ND array output, sort of tensor data. And so, what's the role of static typing in that context? Is it, if I just have one tensor type on everything, am I really adding anything useful? Third is, this automatic differentiation mechanism, and most description of it seems highly stateful, and trying to thread that through the program seems pretty complicated to do with functional programming. Fourth is kind of a practical consideration that even if you can express your models, even if you can implement your models, to train these models is sometimes can be very expensive, and both in terms of time, computation, and dollar amounts, right? So these can take $10,000, $100,000, even millions of dollars to train for these really large models. And some of these large models are what give these neural networks their power. So if you are not able to load these models, these expensive models, you may not, you don't get quite as much use out of it, right? And finally, we can kind of take a incumbent's sort of point of view, right? We can already do a lot with imperative programming, with object-oriented programming. What are some of the benefits of exploring other paradigms? So as you talk about this, I'll try to touch on not just kind of how we do it, but like what are some of the things that are nice about exploring functional programming for this, right? So, all right. So, this kind of this sort of point of view sort of informs the structure of the talk. So I'll talk about sort of each of these items in turn, and starting with kind of what does implementation of a neural network look like from a functional programming point of view. All right. So I've danced around this term of differentiable program, which is really kind of a fancy synonym for neural network. But I like the term differentiable program. And the reason I like it is because as the field has evolved, it's kind of gone pretty far away from the original motivation of simulating the brain and simulating neurons. And there have been kind of different sorts of computations that are used in neural networks, and what works gets kept, and what doesn't work gets discarded. And eventually, you're kind of at a point where what you're really dealing with in terms of the components that make up these neural networks are just mathematical functions, right? So they're mathematical functions that take these tensor data as input and spit out on tensor data as output. And you can kind of see some of these functions here. So to me, what we're doing currently with neural networks is less about simulating the brain. Maybe we converge on some of the ways in which the brain works by coincidence, or just in terms of convergent evolution of how things work. But it's almost more like a new way of writing programs. And it's a way of writing programs with these kinds of functions. And so Chris Olah, a pretty well-known researcher in the machine learning field, kind of put it this way in terms of how he describes neural networks. Is it's something like a differentiable functional programming, where you're looking at the intersection of functional programming with function composition and optimization, right? So, to kind of elaborate on this point of view, this kind of a mile-high perspective on things. So if I can think about a model as kind of a function waiting for an input, and the input it's waiting for is this parameters of the model to fill in, and it returns a function once it has that parameter. And function that it returns is the what in machine learning is called inference, which is you take data in and then you spit out a value. So for example, if this is a computer vision application, maybe what it takes in is a tensor representing pixels in a photo, and the output is some class label of what is in that photo, like a dog or a cat or something, right? So then this inference operation is really just a curried version of the model with the parameter filled in. And how do I fill in that parameter? With some sort of training process where I take in a model, I take in a loss function, which basically takes the output of the model, compares that to data, and basically says how close is the model's output to data. And finally, the data itself, which is takes in some input and output. And it's really that joint distribution between the input and output is what you're trying to match or approximate in your model. And sort of the output of this training is the parameters, which then you fill in to your model parameters. So, so this is kind of like the mile-high view of it. And in Haskell, we can get kind of pretty close to this kind of mile-high representation. So for that model parameter itself, we can kind of think of that and represent that as algebraic data types. And it's quite a natural representation of this, because with neural networks, you're often kind of building up components from smaller components, right? So there'll be a convolutional layer inside kind of a higher level module, or you have fully connected layers that are kind of pieces of other pieces, right? So this kind of recursive structure in an algebraic data type lends itself to kind of piecing together parameters in a model. Furthermore, you can have these niceties of, if I have a sum type, I can use that to represent kind of alternative architectural choices. So for instance, here, I have some part of the model that's representing a sequence, and there are kind of different options for how you model sequences in neural networks. And I can represent that just as a sum type. And if you look at how this is done, say in the Python world, and you sometimes have these libraries that implement kind of these useful architectures, and they're parameterizable in terms of what sort of submodules get used, you'll often end up with kind of this runtime code with all these if statements in it that swaps out sort of different alternatives. And this is one sort of much more natural way of kind of reflecting that. Also, you notice kind of because of that sort of recursive structure in the way you build up neural networks, you can really take advantage of generics to take care of a lot of boilerplate for you. So for example, a lot of the usefulness of generics in serialization, deserialization kind of problems are useful in the same ways here. So for example, I want to pull out all the parameters in all the kind of the pieces of my model. You can kind of use that kind of serialization pattern of generics to automate a lot of things, right? So then the neural network computations themselves, so we talked about kind of the parameter data. The neural network computations themselves are these functions where that take in that parameter as a first element to be queried, right? So here, kind of two examples of a multi-layer perceptron and a variational autoencoder. And these functions are basically written so the last parameter in the output is basically your inference function. So in this multi-layer perceptron, it ultimately takes a tensor input, takes a tensor output. So this is the kind of the untyped version of tensors here. And you can generalize this to this has4 type class. So in PyTorch, that inference operation is usually uses this kind of forward method. And so you can have kind of that same effect here, but sort of represent that as a type class. And that brings me to kind of the usefulness of kind of type class representations for common machine learning patterns. So they're kind of things you do again and again in varying ways, and you can represent that sort of polymorphism in terms of these type classes, for example, for optimization, for unrolling model parameters, to say like update the parameters, or loading data from a data set. And then, once you've done that, you can write against these interfaces in useful ways. For example, with like distillation, I can write a distillation algorithm against has4 type class and so on, right? And so now, since we're implementing the neural network computations as functions, then I can kind of build up sort of more sort of larger neural networks just using Haskell's kind of inbuilt composition, right? So, so what are some kind of nice things about doing this, right? So we can have some better scalability in our code base, right? So as we build up sort of more and more complex machine learning systems, we want to do meta learning, sort of model compression pipelines, reinforcement learning. So things that where maybe I have kind of multiple steps of training, maybe I have load from different data. You can organize your implementations using kind of these nice ergonomics in terms of how you compose these different operations. And another thing that's nice here is that we have able to get a pretty high level of abstraction in terms of how we use, compose, manipulate neural networks, but at like a very low level in terms of the language support, right? So we're using kind of core Haskell features here, and this is quite nice because some of these aspects of composability, you'll get that in certain Python libraries, but if every library kind of has to build up its own kind of set of abstractions for composability, for kind of automating away boilerplate, it's sometimes hard to interoperate with them. And because we're kind of using these really basic language features to express kind of high-level concepts in the way we work with neural networks, it's really kind of easy to interoperate kind of different capabilities that we build out here. And as I mentioned, sort of generics work really nicely in the way we work with kind of parameter data here, and finally, kind of that sort of use of type classes. These are all pretty standard Haskell stuff, but it becomes really useful in machine learning to be able to have overlapping capabilities without kind of squeezing everything into one kind of particular inheritance hierarchy. So, and I've talked about sort of representing neural networks and representing the models themselves. What about kind of the data that flows through the networks in the form of these ND array tensor things, right? And kind of the thinking is, okay, well, if I just put a tensor type on everything, and that's kind of limited. At the same time, these tensors can be really fluid objects, right? Their particular dimensions may depend on the data, right? And as I apply different functions to the tensors, their dimensions change in these computation graphs, right? So how do I use types there? And that's where some of the type level computations in Haskell are really interesting to explore. So all these mathematical functions in the libtorch library, they have sort of implicit relationships between the input dimensions and the output dimensions, and you can make that explicit as these type level functions. So for example, here, this operation sums over one of the dimensions. So it basically integrates out one dimension, and then you're dropping one dimension through the summation, and you can express that explicitly as a type level function. And have that all checked at compile time, and you don't have to hard code like, okay, my kind of input dimension is exactly sort of this numerical value. You're just encoding kind of the relationship between inputs and outputs. Furthermore, these are kind of things that you do at the library level. So someone who's kind of an end user just can come along and take advantage of all the invariants that we've written into the type level representations of these functions. They don't have to kind of figure these all out from scratch. This is kind of in the library implementation, right? Also, convolution arithmetic is something that you do a lot. So convolution operations are pretty common in image processing in computer vision applications. And so you have these operations that they operate, say, on an image, and then the output is also an image, and it applies this sort of windowed filter on that image. And the input-output relationships, it's usually almost the same dimensions, but you have these kind of like boundary effects of padding at the edges of the images. So the output dimensions are off by a couple pixels depending on your filter size and depending on your padding. And it's always sort of a bit of a pain point to do this kind of arithmetic. And again, sort of you can encode that in your type so that you're not dealing with kind of these type errors you're not dealing with these dimension errors at runtime, right? So even though these tensor dimensions are pretty fluid as you go from one computation to the next, there's all these relationships between them, and these can all be captured in the type system. I'll say one other kind of form of type system, sort of type safety you can think about is new types are really handy for dealing with what I kind of informally refer to as like tensor blindness. So you have like functions that it's pretty common in these sorts of functions to have lots of tensor parameters. So you have like just tensor, and you can wrap those parameters in new types that better communicate your intent and clarity, and add sort of another sort of aspect of safety to your code, right? So what we get from this is we get some better runtime safety in terms of your neural network and its relationship to data, and sort of mitigating those sorts of mismatches that you have to deal with at runtime. And you also get nice sort of IDE integrations, right? So your compiler, your IDE knows more about the shapes that your neural network is expecting. And so one of the contributors, Torsten, did a really nice demo at the Berlin Functional Programming Meetup, just sort of implementing a neural network with this kind of typed holes kind of in live programming. And it's really interesting to kind of see all the kind of the hints that the compiler can give you as you write your write your code and implement a neural network. It almost can tell you what to do next, what to sort of fill in next, just by having type information. So that's a bit on sort of type tensors and the use of type tensor data. What about this issue of automatic differentiation? So I mentioned at the beginning, this is kind of one of the core capabilities of that you need in neural networks, because all these optimization functions that you use for the model training are based on gradient computations that you get from automatic differentiation. And this is a whole field in and of itself. And there's I know there's some experts in the functional programming world as well. But kind of most standard kind of descriptions of automatic differentiation, it's very stateful, right? And it requires constructing kind of this computation graph that you need to build up. So every kind of function calculation that you apply, you add a node to that graph. And to carry this around seems very difficult to do if you're kind of in this functional context, stateless, trying to program in a more stateless way. And so this is an active research area in terms of how to do this with functional programming. You know, there's papers on this, and actually kind of our first implementation of automatic differentiation in Hasktorch, Sam Stites implemented using this backprop library by Justin Lay that sort of explicitly represents that sort of differentiability aspect of these computations. But with the release of libtorch, there was a simple option that we've implemented that can provide a pretty simple interface to automatic differentiation. And this is a bit of a luxury we have because there's already a underlying implementation of automatic differentiation in the C++ library. And so one kind of way of providing a simple interface to that is just to kind of get the semantics and sort of interface to automatic differentiation, right? And handle sort of this kind of the stateful aspects of the constructing compute graph sort of below the line of abstraction. So you can think of it this way, which is that sort of requesting a gradient by itself doesn't have any effects, right? But if you kind of treat it as instantiating independent variables, so the variables with which you're taking the derivative with respect to, so those, if you treat those as effectful, then everything else you can treat as pure. And so, so when you're doing these computations, when you kind of apply a function that's in libtorch, under the hood, there's sort of this compute graph being constructed. But to you, it just looks like, oh, okay, I'm adding one tensor with another tensor, and I'm taking the mean of this tensor, and those look like stateless, pure functions. And so just by combining those two things, right? So instantiating independent variables is an effect, and then everything else is pure. You're able to get this pretty simple, clean interface to automatic differentiation, and that's something that we can we can take advantage of libtorch to do. But there's some trade-offs to that for it to be this simple, and there's still a lot to explore in terms of how can we represent automatic differentiation in a functional programming context. So the last point, I want to touch on is interoperability with PyTorch, right? So we have these, large expensive to train models that are in PyTorch and that are kind of been trained in Python. And we don't want to be in an island in Haskell because those kind of pre-trained models are really useful. And we don't have to kind of retrain, get the funding or whatever to retrain them all from scratch. And fortunately, we can kind of piggyback on this trend in the productionization of neural networks, which has produced these kind of IRs and serialized representations of models, right? So Torch script is this kind of IR for PyTorch models. And so we can just take advantage of these serialized representations of models and load them into Hasktorch. And so from there, we can kind of pull in parameters that may have been trained from a $1 million training process and load them into Hasktorch. There's more to do to kind of make this smooth, but sort of we've had a few proof of concepts, and it's very feasible. And I think there's a lot of value add there because now you can start from a pre-trained model and not have to start from scratch in your training. And you can apply all these kind of transfer learning mechanisms and things like that if you're able to deserialize load models that have been loaded in PyTorch. And so we're no longer just kind of an island where we have to kind of recreate the universe from scratch in Haskell. So, so that's a very high level view, introduction of kind of like the big picture view of how we think about the library. And so for people that are interested in getting started, just want to give a little bit of a tour of Repo and entry points and what to look at. So kind of a starting point, if you're looking at the repo, is pulling in some of the dependencies. So this libtorch library, downloading that. So there's a script inside this dependency directory to take a look at first and pull in those dependencies. Start off trying to run and build some simple examples, like a simple linear regression, make sure that works. I have support for Cabal, Stack, Nix, and Stack's probably the simplest, but has some limitations. Nix is pretty powerful, but has a pretty steep learning curve. So none of them are kind of perfect yet. One of the complexities here is there's this kind of shared libraries that get pulled in. So if you do run into trouble, definitely ping us on Slack and if you need help. And you can also kind of refer to some of the continuous integration scripts up here, which do have kind of step-by-step code for Linux, for Mac, etc. But definitely ping us on Slack if you run into any trouble getting started. There's a really nice community that's kind of forming around in data Haskell and in data science and machine learning Haskell, and Hasktorch contributors is really everyone's super friendly. So we have a Slack you can come join, and so feel free to take a look at the repo, and you can email at that at this email here and come chat with us, and can follow up, ask questions, and happy to have other people come help join the project. All right. Well, with that, thanks for your time, and I'm happy to take any questions.
Thanks for this great talk, Austin.
Thank you.
Is at least one question on Slack already. It's kind of a discussion, free-form discussion question. If you're here, you can also unmute yourself and ask it.
Sure.
Yes.
So people usually make do with the type level programming facilities of Haskell because they want access to other existing Haskell. But if you're starting from scratch, right? Like you're building an SSI interface to PyTorch, and you're gonna use Haskell basically as your host language for building these networks. So in that case, why not go with a proper dependently typed language where the type level programming is not going to be painful? So why stick to Haskell?
So you're saying in that case, why not go with a what dependency stack? I didn't get that last part.
I mean, like, just go with a properly dependently typed language. So instead of going with Haskell and having to write close type family versions of all your functions, etc., why not just go with a dependently typed language?
Oh, dependently, like Idris or something like that.
Yeah, exactly.
Oh yeah. I mean, I'm sure that I'm sure there's a there's probably a appetite for Idris Torch at some point. Certainly, yeah. So there's some trade-offs, right? Like Haskell's dependently, implementation of dependent types is is sort of like kind of evolved over time versus kind of built from the ground up. And yeah, it's probably kind of an interesting space to explore of like if you have kind of a purely kind of dependently typed language, like what do neural networks look like there? I'd say there's some benefits to kind of Haskell being around longer, having kind of broader ecosystem to interact with. But that's probably something to explore too. Is maybe when Idris 2 is further along, could be a cool project. I will say one thing which is that for kind of the subset of dependent types that we've needed to use is pretty basic, right? So it's a lot of these kind of like dimension calculations and things like that. So for that, Haskell's sort of subset of dependent types covers a lot of what you need, but maybe there's some other ideas that we haven't explored just because it's trickier to express.
No. What I meant is that on the term level, so you're saying that you're using Haskell, and one of the benefits of it you just said is that you do have access to this ecosystem of normal term level Haskell libraries. So could you maybe say some words about what that looks like? So like what is like in an application where you use Hasktorch, what else is that program doing other than just building a network and then training?
Yeah. Right. I think a lot of that is kind of to be explored more and more in the future. But I would say this is that, it's true. Like right now, when people think of like machine learning, they kind of think of this like sort of like one shot, like, okay, I implement my model, I train my model, and then, I perform inference. And I think there's like, there's a lot more sort of ways of being creative. Like, so things like there's kind of subfields of machine learning around like meta learning, where you may have kind of like all different kinds of data and you're kind of trying to figure out like what sequence of training, and what sequence of computation sort of like makes learns the fastest, right? Kind of another thing is things like model distillation, model pruning, where maybe I train a model and then I kind of compress it down to like a smaller model because it's more efficient to compute those inferences on, so that I have kind of a faster application or kind of when I'm just doing. So there's kind of I think kind of like as the field's moving, you get kind of further and further from the just like, okay, all I need to do is train and do inference, right? There's kind of like multiple steps of things you can do, creative things you can do, in ways in which you can embed learning processes in an application that in some sense haven't been explored all that much, because does get pretty cumbersome to implement something that's more complicated than just, okay, train and compute and inference. One kind of like pattern or maybe anti-pattern I see in some of the Python ecosystem is like when you start to get to these more like complex things, like there's a tendency to make it so that like, okay, I have this sort of multi-step complex process, and the way you interface with it is through this like JSON configuration file. So right, so you're just writing kind of processes in terms of JSON configuration files for example, model distillation. And part of that, I suspect part of the reason, people just kind of becomes like, okay, code your machine learning stuff in a configuration file, is because it's hard to kind of like, scale up to kind of these meta processes. It's just kind of a little bit cumbersome to do that. So So yeah, I think there's a lot to explore in terms of kind of these building more systems and applications that have training inference as part of them, but isn't just kind of like this one stop. I just train my model and I'm done kind of thing.
Great. There's another question by Heinrich.
Hi, I'm Heinrich. I have a question. So, kind of related to the previous one. So, the Haskell type type algebra can be a bit intimidating at first, and I was wondering if Hasktorch takes or if it does take a kind of a modular approach, that you have this high-level typed interface where you can specify the dimensions of the tensors very precisely and get guarantees in your type system about that. Or if you are not inclined, if you on purpose do not want this, if you're fine with going a bit untyped, does Hasktorch offer both approaches, that you have an untyped version and the compatible typed one?
Yeah, that's exactly the approach we've taken, right? So you can write models. You can do everything you want with respect to kind of untyped tensor, where you just have a tensor type, and maybe you can just wrap new types around it a little bit, but your program's just sort of ignorant to dimensions. And then there's kind of the typed interface, and there's a little bit of exploration as well in terms of kind of something that kind of straddles in between those two, right? So you could think of maybe some sort of like gradual typing kind of perspective, or something that maybe you have kind of some maybe cast between them. But that's that's I would say kind of open for research. So definitely that's kind of the perspective we've taken as well. That not everyone, on one hand, not everyone kind of wants to do type level computation and things. But it's also there for people to contribute to and explore as well.
Yes, I see. Great, thanks.
Yeah, and actually, if some of the slides, you'll see some of them just have kind of opaque tensor types. So there's some examples in the slides of both.
Right.
Okay, are there any more questions? I don't see any more in Slack or any other chat.
And feel free to ping me in the Slack, or email me, or ping me on Twitter as well. So happy to chat more later.
All right, in that case, thanks again to Torsten for this great talk. I can see that you're still drinking coffee, because it's probably still quite early at your time.
Thanks for having me.
Yeah, and thanks for everyone listening. And have fun with the finishing hours of the Haskell, of the MuniHac conference.
Right.
Yeah, we can see each other in the break rooms, in the virtual office, or in Slack. Keep in touch. Okay.
All right, thank you.
And this meeting. Bye-bye.